Okay, good morning. Um, I hope you had a good weekend. Before we get started, just a couple of reminders. You got your third problem set. I've moved the problem sets due dates. I haven't maybe updated it all throughout the or the Moodle page, but the expectation is that the homework's due on Tuesdays. And don't forget that I've expanded office hours. So if you need that, make sure you use that. Um, Hopefully this week isn't too strenuous. I think there's only 5 problems, and that's because we have the first midterm this week. Um, so the first exam is on Friday. I'll open it up. Hi, everybody. I'll open up the midterm Friday at class time, so at 10 o'clock. And it'll be 4 questions. Assuming I have some time today, I'll put up some sample questions, but it'll be similar to stuff that you've done in the homework, but a little easier to do in the allotted time. Before questions, you can choose 3. They'll be based on problem sets 1, 2, and 3. And while I'm hoping that I've written this exam to be done in an hour or so, I won't post the solutions until 5. So if you have other obligations, you can't quite get to the exam right away, fine. If you need to take a break and come back to it, fine. But if you have an uninterrupted hour or so, it should be okay, is my plan anyway. This, in terms of what I've planning on asking. I haven't quite finished writing it yet, but it's not too dissimilar from what I've asked before. So I'll post a sample, either a set of sample questions or the midterm that I gave last year at this time, or not last year, last time I taught this. So you have an idea of what I'm asking. Okay. Any questions about the exam or anything like that? Okay. If not, or if you do, make sure you get to me. Today, we are starting the next section, which is differential equations. And today is just an introduction. I think a lot of the first part of it you'll have seen before, and then we'll move on to increasingly more complex differential equations and solutions to those, and partial differential equations. And also, while some of the first examples will be strictly mathematical, we'll be going more and more into physical applications of these differential equations, some of which you've seen, some of which you've heard about. Also based on at least 1 and maybe 2 persons' questions about Fourier series, I have another example of how Fourier series shows up in something like the Laplace equation that I'll post today. Actually, it's in the heat transfer equation, steady state heat transfer equation. So I'll give you another idea of how you can use the idea of Fourier series to solve those partial differential equations. So I'll have that up today. And just a reminder, please fill out those reflections, because that gives me an idea of what to post in addition to these lecture videos. Okay. All right. So again, we're doing differential equations, and we'll start straight off with a usual set of definitions and nomenclature. We'll be focusing for at least the first part of this on linear equations. Linear equations just mean that we can write the terms of the equations as some either constant or function times increasing powers. And here we're just assuming that these are in this simple case. So this is 1. Y is a function of x, though we'll certainly look at different cases of that. We know also in the case of linear functions that if we have, say, an operator that represents differentiation or differential equation acting on, say, A phi times B psi, that's the same as A times L phi plus B times L psi. These are constants. All right, so they're just linear operations. We also often define these by their order. That's just by the highest non-zero derivative. And then we have ODEs and PDEs. You all know what these are, right? So the reason why I bring this up is that there are different classes in particular of partial differential equations that we'll look at in the next couple of weeks. The other thing to remember too, even though the homework for this week is due on Tuesday, your next homework is not due for another 2 weeks because you have an exam on Friday. So you're not, hopefully you're not just spending this week rushing to do 2 problem sets. Okay, you're studying for the exam. All right, so we have different classes of partial differential equations, and they're divided sort of the same way that we did with say, ordinary differential equations by the way that they, excuse me, by the nature of the relationship with their independent variables. So, for example, we have elliptic partial differential equations, and the best example of that would be Laplace's equation, say in 2 dimensions. Oops. Right. In other words, the derivatives in this case look like the equation for an ellipse. We also have parabolic. And in that case, that might be something more like Schrödinger's equation. So h bar minus h bar squared over 2m del squared plus v times psi is equal to I h bar d psi dt. Where you have mixed order. So say first order in time, but second order in space. And then, as you might guess, you have hyperbolic PDEs. And a good example of that would be the wave equation. So 1 over c squared d dt squared, that's a t, minus del squared psi is equal to 0. So that in that case, both time and space are second order. All right, so we'll get to methods of solution for all of these. We already know one, namely separation of variables. And we looked at one of those last week. The last thing I want to say before we get into actual differential equations are the different kinds of boundary conditions. Right? And typically, we are looking at second order differential equations, which means we need 2 sets of boundary conditions or initial conditions. So we've seen some. So let's see if you remember, what are the Dirichlet boundary conditions? What do they specify? On a boundary. So you would have seen these in E&M when you were solving Laplace's equation or looking at electric fields, looking at Gauss's equation. So what can you specify on the boundary? What would be the most straightforward thing that you could specify on the boundary?
0.
Well, in fact, the actual value of the function, right? So a differential equation that has specified on its boundary the actual value is called a Dirichlet problem or Dirichlet differential equation. Then you have the Neumann boundary conditions. And you definitely saw those in E&M when you looked at, say, electric fields on a boundary. So rather than having the actual value of a function on a boundary, what could you specify instead? Or some condition of an equation or a variable. If you know the electric field on a boundary, what does that tell you in E&M? Oh dear. Let's think back. What is the electric field going to depend on?
Charge distribution.
Ah, yes, the surface charge distribution, right? So the Neumann, if you remember, the Neumann boundary conditions are when you specify the normal of the function on the boundary. And remember that the normal of the electric field on a boundary is proportional to the surface charge density. I don't know if you remember that. I actually don't remember that all the time either, so don't feel too bad if you remember that. So, but generally speaking, the two types of boundary conditions that you have for differential equation are Dirichlet problems or Neumann problems, and then occasionally you have Cauchy problems, and these are just combined. So you might have the value of one variable and the normal of another variable, the normal derivative. Okay. That's all set up. So let's get to actually looking at differential equations and start with the ones that you know the best and the ones that you've seen before, that is first order ordinary differential equations. Right? So these have the form, if we're going to follow sort of the convention of your book, that we have dy dx is equal to some function. And we can write this as minus p of xy over q of xy, where p and x, or p and q are functions. And the trick behind this is that we hope that these are separable, right? So in the easiest case, both p and q are only dependent on one of the functions, namely dy dx equal again to some function, but is equal to the ratio of p of x and q of y, which means that if we expand this out, we can write p of x dx plus q of y dy equals 0 in the simplest case, in the homogeneous case. And that means that we can evaluate this over x, p of x dx plus the integral over y of q of y dy, and set that equal to 0. right? So, I mean, that's obviously the easiest case that we can handle. And the examples of that are multitudinous, as I mentioned at the beginning of class. The easiest, and probably the first one that you run into, is radioactive decay, right? Where you have the derivative of the number of a population with respect to t is equal to some decay constant, or minus some decay constant lambda times n of t. It is the population rate is proportional to how much you have there. And all that B3 is saying is that you can safely rewrite this as dn over n equal to minus lambda dt, right, which gives us the natural log of n is equal to minus lambda t plus the log of n naught if we're integrating from some initial period or initial time, or famously n of t is equal to that initial population times e to the minus lambda t. And again, we could do the usual, right? We could check to make sure that lambda has the right units, should have inverse time, right? We could write this as 1 over a half-life, right? Or 1 over an ETH life for E folding time. And we could check the limiting behavior. But again, this isn't anything new. The other example is free fall. In a viscous medium, in which case we're going to assume that the equation of motion ma in one dimension is equal to mv dot, which is just mg minus v squared. So actually, let me get this 8.4 and 8.5. This is not anything that you haven't seen before. If maybe the last time you saw it was comp mech, but I'm going to recast it a little bit. We know that this means that we have terminal velocity. And in fact, we can compute the terminal velocity without doing any calculus. How do we find the terminal velocity? What's the condition that's met for terminal velocity?
A equals 0.
Right, when there's no acceleration. And so if we do that, we know that the terminal velocity is just equal to v squared is equal to mg. So v is equal to mg over v square root of tau. And that should also be the velocity that the answer that you get as time goes to infinity. Okay, so this is something that we can easily separate. So we can separate v and t. And when we do that, we have dv is equal to g minus v over m v squared dt. And of course, we can check the units for b. This gives us dv over g minus b over m v squared is equal to dt. And so we can write, sure, I'm careful with this. A couple of ways we can do this. Can write this as the integral over v of dv prime, I'll use dummy variables this time, over g minus v over m v prime squared. and that's equal to 1/2 m over GB times V naught, no, not V naught, V tau plus V tau minus V is equal to T. Right, where I've just rewritten the 1 over G minus B divided by m times E prime squared in terms of that terminal velocity. What this does for us, I think if I got this right, is to solve for V in terms of e to the 2t over capital T, that is sometime t later, or some fiducial t, I should say, minus 1 over e to the 2t minus capital T plus 1 V naught, sorry, V tau. I'm mixing up my notation, I apologize. Equal to V tau times sinh of T over capital T over cosh of T over capital T, or V tau is equal to hyperbolic tan of T over capital T, where T is equal to m over GB square root. That is the time to drop your velocity by a factor of e, your e folding time. So when I've done this in like comp map, we just left it in terms of the natural log and then expanded that out and see what happens with when time goes to infinity. If you just write it in terms of, the reason why I did all of this up here was to write it in terms of these hyperbolic, this should be a sinh, hyperbolic functions, and then you can see that when t goes to infinity, v goes to that terminal velocity. Okay. Another thing that you can look at, and you can either do this at home or I can do this in another example, is to do the same thing, right, for the non-turbulent regime. So when the viscous force or the resistive force is dependent only on V rather than V squared. That's a little bit more straightforward, as you can imagine. Okay, let's give you a break. Any questions so far? Okay. All right. We're all ready. We want to turn our attention now to what are called exact differential equations. And we'll stay here for a little bit and look at a couple of examples and one circuit example. So the definition of an exact differential takes us back to how we started this conversation in the first place. Remember, we started by saying dy dx is equal to some function, and that we can break this function up into a numerator and denominator, p's and q's. Right? And then we focused our attention to the special case when p is only equal or depends only on x, and q is only dependent on y. So we can imagine that we start with an expression p of xy dx plus q of xy dy and set that equal to 0. So this is just a general statement. We'll call this exact if we can define something d phi as the usual way that we would break this up with a chain rule. In other words, if we were to look at d phi, we knew that phi depended on x and y, we could write that in terms of a partial with respect to x, and then the exact differential dx plus the partial of phi with respect to y times the exact differential with respect to y. And the idea is that we can then identify our Q and our P as that, right? So it's exact if it's equal to this. In other words, again, this is a little bit repetitive, d phi dx is equal to P of x, y. So far, we're not making any statement about whether P is only x or only y. Right, so we're being as general as possible. Now for this to work, the necessary and sufficient condition, and this is independent of order, is that the cross terms don't matter. In other words, especially if we're looking at how we would differentiate with respect to y and x, say d squared phi dx dy equals dp dy equals dq dx equals d squared phi dx dy. Okay, so we can start with saying an exact differential equation is one of the form, however you like to write it, either b.6 or b.7, and part of that means that these cross terms are equal. That means that if there is a phi of xy, then phi is equal to a constant. In other words, if there's a solution to this kind of equation, then the actual solution is a constant. But if it's not exact, we can fix it, right? So clearly, not all differential equations are exact, right? These are very special and stringent conditions. So if the differential equation is not exact, what can we do? So if not exact, how can we bend this to our will? What do we use? What might we do, or what's a possibility? What's something we could do to try and make this exact? That wouldn't change the equation. Remember, we're considering what if b.6 is not exact? What do you do with an equation that that doesn't change the value of the equation, or what can you do? You've done this. I know you've done this. Say you've got an equation, you want to make it more malleable, so you do something to it, doesn't change the equation at all.
Separation of variables?
Well, eventually, but let's even think about just basic algebra. What can you do to an equation that doesn't change the equation?
Multiply it by 1.
You could multiply, in fact, since this is set equal to 0, I mean, it doesn't really matter. You could multiply it by anything on both sides of the equation, right? In other words, we can use what's called an integrating factor. Has anybody heard of integrating factors before? Maybe a little bit? Okay. So if it's not exact, we can make it exact by applying the same integrating factor, say alpha of xy, and multiply it across the board. So we multiply it times p dx, and we have alpha of xy times q of xy dy. And of course, it doesn't matter on the other side over there. That's still 0. And the idea is that we choose our alpha so that we can make it exact. So, for example, let's look at x dy minus y dx is equal to 0. This is not exact. And the reason why you know it's not exact is if you were to take dp dy, that would be equal to minus 1. And if you took dq dx, that would be equal to 1. Right? Now, if on the other hand, if you chose alpha of xy to be 1 over x squared. Why? Because you happen to know the answer to the problem. That's the problem with integrating factors, is that they're useful, well, always true, seldom useful, right? It's hard to know what the integrating factor is ahead of time without a lot of experience. So in this case, if we use 1 over x squared, we have x dy minus y dx over x squared. That's equal to 1 over x dy minus y over x squared. Dx is equal to 0. Is this exact? Well, dp dy is equal to minus 1 over x squared. dq, dx is equal to minus 1 over x squared, so it's exact. And what we know then is dy dx is equal to what? What's our definition from starting down this road? We go all the way back up. Why do we start with p's and q's? What's dy dx equal to?
Negative p over q.
Go ahead, Nick.
Negative p over q.
Right, minus p over q, which is equal to 1. So that means that y over x is equal to a constant. And if you check back over here, that's the solution to that differential equation. Okay? So the reason why you would try and make this exact is because your ratio of P over Q is going to be a constant. Once you've found out the relationship between y and x, now you have your function y is equal to cx. Right? So if you plug this in, y is equal to cx up here, right? Then you'll see that that's equal to 0. Everybody follow? Yes? Okay. All right. Okay. Our next thing is gets a little hairy with the math, but in fact is the thing that you are probably most familiar with, and that is linear first order ordinary differential equations. Right. So linear first order. And you've been fortunate enough, probably in most of your physics career, that the differential equations that you deal with are either so easy, or not so easy, but they are either ones that you recognize because you see them all the time, or they are so difficult that you just pop on the Wolfram and solve it anyway, right? So what we're going to do here is suggest a way of solving almost all of these. So let's start with our definition. So if we have a function of x and y, set that equal to, again, using the same nomenclature from earlier, minus p of x, so purely of x, times y, plus q of x, then dy dx, oops, plus p of x, y is equal to q of x. Right? So that's our linear first order differential equation. It's homogeneous, and we're very lucky if q of x is equal to 0, and inhomogeneous if not. But it, frankly, we can get by if it's not homogeneous or inhomogeneous with a judicious use of an integrating factor. So one of the reasons why, excuse me, I started with the exact differential equations and went into this sort of subtangent on integrating factors is because you need them here. And so the general solution then, and hopefully we'll get to a couple of examples of this, is to use that integrating factor and our definition of B point 13. So let's have alpha of x. This time we're just dealing with first order ordinary differential equation. Multiply that through, so we have alpha of x dy dx plus alpha of x p of x times y is equal to alpha of x times q of x. Right, we haven't done anything special. All we've done is take B13 and multiply it by an integrating factor. Okay? But we can look at that and realize that this is d dx of alpha of x, y, and set that equal to alpha of x times q of x. If we're careful about how we solve for p. So this is B.15. In particular, we can look at alpha of x dy dx plus d alpha dx y. Set that equal to alpha of x, q of x. We're just expanding out B15. And what that means, if we identify the components in B16 with the components in B14, we have d alpha, that's an alpha, sorry, be more explicit, d alpha dx is equal to alpha of x times p of x. Right, that means that alpha and x are separable. And that means that the solution, the way we go about solving this is we created a differential equation for alpha, and then we solve for alpha, and then we put that back into B14, essentially. So what does that mean? That means that if we look at this, we know that alpha of x is equal to, the solution to this is equal to the exponential. Again, I'm going to use this notation. The integral up to x just means I'm using dummy variables here. P of x prime dx prime. Right. So that'll give us some functional dependence of alpha of x. And then that means that we can integrate our previous equation. So now we have the integral over x of d dx of alpha of x prime, y of x prime, d of x prime. Right? Is equal, so that's, we're doing this up here, right? Is equal to the integral over x of alpha of x prime, q of x prime, dx prime. And so because we're taking the integral of a derivative, we're basically going to pop out alpha of x, y of x is equal to the integral over x of alpha of x prime, q of x prime, dx prime, plus some constant, if we're being honest with ourselves. Those will include like initial conditions or boundary conditions. Then we basically divide by alpha, right? Because what we're after is y of x. So y of x is equal to alpha of x to the minus 1 times the integral over x of alpha of x prime times q of x prime dx prime plus c. So if we put this all together, and I know this is a lot of writing, we can have our final form, which is y of x is equal to the exponential of minus the integral of p of x prime dx prime times this bracketed term. The integral over x of ex, or e to the, again, integral over, we're going to be using lots of dummy variables, z p of y dy q of z dz plus c. I think I've closed off all of those parentheses. That should be a bracket. Okay. So that's a lot, and we'll look at a couple of examples. But the main idea here is to recognize when you have this for first order linear differential equation, and then find your p's and q's and alphas. Right? We know too that, and we'll look at a couple of examples about what happens when you have a homogeneous case, in which case we know that q is equal to 0, right? Or the inhomogeneous case, in which case you need to include that q. But B21 is the key to basically solving, potentially at least, any first order differential equation, ordinary differential equation. Okay, so let's get an example. Let's first look at just a mathematical example and then a physical example. Let's say we have x squared y prime minus 2xy is equal to 1 over x. Right? First order linear differential equation, ordinary differential equation. What's our first step?
Identify P and Q.
Right. So the best way to identify P and Q is to divide by, in this case, 1 over, or divide by x squared. So this is the same as y prime minus 2 over x, y is equal to 1 over x cubed. All right. Now we have our linear first order ordinary differential equation, right? So in this case, P is equal to what?
2 over x, negative 2 over x.
All right, minus 2 over x. Q is equal to
1 over x cubed.
1 over x cubed, and then alpha is equal to 1. Okay, so if we do the integral of P over x dx prime, we get the integral over x of minus 2 over x, and that's minus 2 times the natural logarithm of x. But we need e to this integral over x of minus 2 over x prime dx. That's equal to e to the minus 2 ln of x, and that's equal to 1 over x squared. Okay. Then if we look at B21, we have the formula for how we would solve this. Namely, in this case, y of x is equal to e to the minus that integral of minus 2 over x times all of that stuff that we have in the brackets up the page, up here. So this is equal to x squared times the integral over x, because we're flipping over that integral, times 1 over x squared times 1 over x cubed dx. I guess these are all primes, is equal to x squared times the integral over x of x to the minus 5 prime dx. And oh, and then we have the constant in there, right? So that this ends up being y of x is equal to minus 1 over 4, because this ends up getting evaluated and then multiplied by x squared, right? So this becomes minus 1 over 4, 1 over x squared plus c times x squared. I think the thing to remember is that we have x squared times the integral of that. That gives us the x to the minus 4 plus a constant, right? So our solution to that first order differential equation should be essentially a combination of x to the minus 2 and x squared, and I'll leave it to you to plug that back in up there to verify that that's the correct solution, which, if you have time, is what you should always do with these. Okay. All right, another example. This one's more of a physics example. Let's have an RL circuit. So some resistor R, an inductor L attached to V. And we can write the differential equation that represents the current as a function of time as L times I dot plus RI is equal to V. In other words, that describes how the voltage changes across the circuit. Our first thing to do here is to identify everything. And again, if we divide by L, right, we can see that P is equal to R over L, and Q is equal to V over L. Then our alpha of t is equal to the exponential of the integral over t of R over L dt, or e to the RT over L. Then if we go to our version of B.21, I of t now is equal to e to the minus RT over L times the integral over t of e to the R t over L, this is t prime now, times v of t prime over L dt prime plus c. And just to point out, this is alpha to the minus 1. This is alpha, and this is q, right? And we've already embedded the p when we calculated that alpha. All right. If we make this easy on ourselves, let's make this a constant potential, so it's not alternating. We have I of t is equal to e to the minus RT over L times V naught over L times L over R times e to the RT over L plus a constant. And that equals V naught over R plus some constant times E, and I'll write this a little bit differently, minus to T to the minus R over L. Oops. In other words, our current is equal to what we would expect plus some exponential decay term. Right? And if we check the units, then we can see that's they're what we would expect. And for t much greater than L over R, we would get Ohm's law. For t much less than R, we get something that varies linearly. In other words, you should convince yourself that if you were to plot current as a function of time, for small time, essentially you get a constant or a linear increase in the current, and then eventually at large time, since you have essentially Ohm's law, this rolls over to a constant. Okay. And I think this example is in your book. In your homework, you have a population question. I think something that looks like, so in your homework, you have something that looks like dn d2, dn sub 2 dt plus lambda 2 and 2 is equal to lambda 1 and not e to the minus lambda t. In other words, it's a double decay. And basically what you can identify is that this is your y prime. This is your p times y. And this is your q, right? And once you know your p's and your q's, you can calculate alpha. And from that, you can use b.21 to solve the differential equation. In this case, population n sub 2. And I think it's the second or third homework problem. Whew. Okay. We have a couple of minutes. Rather than launching into anything else, let me, before I ask you if you have any questions, just recap where we've been today. Right. So all we've done is define differential equations, first order differential equations. We looked at separable equations. Right. We've introduced things like the different kinds of boundary value problems we're going to have. And the main thing that we did today was start with what an exact differential equation is, or exact differential is, and then use that to create an all-purpose general way of solving any linear first-order differential equation. Right? As long as, now the trick, right, is that you're assuming that you can do the integral, right, to find alpha. Right? It's entirely possible that the p that you use that goes into solving for that integral is either intractable or is not as nice and clean as the two examples I did today, or the one that you'll see in your homework. But it's at least something that you can write out. All right. Are there any questions about what we've covered today? How many people have seen this method for solving first order differential equations? Okay. Again, it's in the very first part of this section in differential equations, so I would read over it again. It's extremely powerful, and it sets the basis for how we're going to proceed with some of the other different methods of solving differential equations on Wednesday and then next week. Okay, so everybody take a deep breath. Make sure that you look over the homework, make use of office hours. I'll get some supplementary material for the midterm on Friday. If you are at all concerned about the midterm, make sure that you contact me. You guys are going to be fine on the midterm. You're going to have plenty of time. And as I mentioned at the beginning, for those of you who missed it, and I mentioned this last week too, the midterm's open book and open notes. So you have essentially unlimited time and unlimited resources, as long as you're not looking up something online, to do this midterm. And that doesn't mean that I've written something that's impossible to do. Just to cover that. So it's a regular midterm, but it recognizes that we are taking this regular midterm under unusual and irregular circumstances. Okay? All right. Well, if there's nothing else, all right, I'll see you later then. All right. Bye, guys.
Bye, Meg.
Bye.
Bye.
Bye, Allie.